In example 2 here, we want to take an inverse. Remember that, the basic idea behind an inverse is that we could switch x and y. And at that level, if that's all we knew, we could absolutely move this graph around and we could find these new coordinates. I mean, I could take this coordinate, which is at, for example, -7, 2, and I could inverse this, switch x and y, and it would quickly become, for example, 2, -7. And I could do that for a series of coordinates to start to get this picture. The intent of this example here is to kind of talk about a little bit of domain and range and to be able to understand how, when reflected, remember the line of reflection is going to be on this diagonal, a perfect line, y is equal to x. And let me just kind of make that stand out a little bit better here. There it is, there. That ends up being our line of reflection. Now, when this happens, when we switch y with x, we can expect a bunch of different things. Now, the true test for a function, the test for a function, come on, go back. The test for a function is usually, almost always, what we call the vertical line test. That's typically what we would go to when we want to test something to be a function. But if I don't know what the inverse looks like yet, we have a little trick up our sleeve to say that we could use a horizontal line now, because after the inverse is taken and after the reflection is taken, that would turn into a vertical line. Okay, so what I'm saying is that a horizontal line would turn into a vertical line when we do the inverse. And so if I do the horizontal line now, before I've taken the inverse, it has the same effect as doing the vertical line test later. And it's a little bit of a trick up our sleeve to kind of maybe predict the future. And so as I use a horizontal line on this graph, you can see that, as I scan this graph, it does touch more than once. So I think the inverse will fail our vertical line test. This is a way of predicting. It seems, there's lots of intersections. And so explain why the inverse is not a function. Without even seeing the inverse, I could kind of explain this. I could say the inverse, or the horizontal line test, touches more than once on the original f of x. Therefore, the inverse will fail the vertical line test. Sorry that I'm writing so small, I just didn't leave myself much room. That could be a way of kind of explaining my logic here. And the same for the domain and range. The original graph that's over there, I can see it. Domain and range is really convenient if you can see the graph. I don't know what the inverse looks like yet, but I can predict it. It looks like the domain of this graph goes between -7 and 10, and the range of this graph goes between 0 and 4. So I would assume and be able to confidently predict that if we're going to inverse this information, that the domain and range will, like coordinates, all x's and y's switch. And so I would be able to predict the domain is 0 to 4, and the range is -7 to 10. And let's see if all of these predictions work when I move all of these coordinates. Like -2, 0 becomes 0, -2. 6, 4 will become 4, 6. Oops, I don't think that was right. 6, 4 becomes 4, comma 6. Yeah, that's where it is. 4, comma 6. And then 10, comma 1 will become 1, comma 10. And if I draw this out, let's make this stand out. I think everything is what it was expected. This does not pass the vertical line test. As you can see, vertical line fails this graph. As you can see, the domain checks out, 0 to 4. The range checks out, -7 to 10. And all is good. And that's a really nice reflection. And this is the graph that we would call f of -1 of x, the inverse function. And I do see an invariant point. That invariant point was on the line of reflection, and it looks like 2, 2 was the only coordinate that didn't move.